In the previous video we were dealing with the exponential decay of carbon-14 and we calculated one of the parameters. We calculated B. Now, if the Shroud of Turin was 2000 years old, what percentage of carbon-14 must be left in it for it to be believed to be authentic? We know that at time 0 Q is equal to A. That's just this number here, whatever A is, and we're interested in seeing what the value of Q is at 2000 years. Let's suppose 2000 is about here. I don't know where it is roughly in the scale of things because I don't know what A is. We will be interested in the percentage of it left, so we want to compare this value to A. Basically we will be dividing the quantity at 2000 years or after 2000 years by the quantity initially, Q of 0. So we will get this number as a percentage of this number. Once we have this ratio, we multiply by 100 to turn it into a percentage. So Q at 2000, let's get an expression for that. So here's Q of T, so we just plug 2000 in for T. So we B times 2000 or 2000B. And we want to divide it by Q at time 0, which is A, and then multiply this by 100. Now I've just plugged in for B here. This is B, and we need to calculate this. So you see, it doesn't matter what A is. This percentage will come out to be some value because the A's cancelled out. To 2 decimal places we get 78.51. So actually this point here is about 3/4 of the distance from 0 to point A. It's 78%. So this diagram isn't too accurate. So this is a more accurate picture of what's going on. So when T equals 2000, the value of Q is 78.51% of A, or 0.7851 times A. So this is the percentage of carbon-14 that will be in the Shroud of Turin if it really is 2000 years old. Of course, if it's less than 2000 years old, we would expect to find more carbon-14. We would expect this percentage to be larger. We would expect the percentage of carbon-14 to be larger than 78.51% if it's less than 2000 years old, which it actually is. See part 2. If the actual percentage of carbon-14 in it is 93%, how old is it to the nearest year? So, here's the picture. We're interested in Q, a value of Q of 93% of A, that is 0.93 A. And we're interested in the value of T that corresponds to 0.93 A. So we have to find out what this value here is. That'll give us the time taken for Q to go from A, the initial quantity of carbon-14, to 93% of A, or 0.93 A. So we set Q of T, which is AE to the power of BT, equal to 0.93 A, and we solve this equation for T. You can see that it doesn't matter what A is, we can divide that both sides, so we need to find out what T is. We know what B is, we have that value, I'll plug that in later. To solve this equation we get the ln of both sides, so we've done this before. Ln of e to the power of something is just a power, so we can now solve for T. So what I'll do is I'll get the log to the base e of 0.93. I'll multiply above and below by 5730 and divide by ln of 2, or minus ln of 2. To the nearest year you get 600 years. So the value of T is very close to 600 actually, it's 599.91. A table of the quantity Q in milligrams of carbon-14 found in the shroud every 1000 years is given in the table below. So we want to calculate ln of Q to 2 decimal places for each of these values of Q. Next we're going to look at a graph of ln of Q against time. So here I've roughly plotted the points from the table, and as you can see, it looks like they lie along a straight line. As a matter of fact, in theory they should lie along a straight line, because if we look at the function q of t, it's ae to the power of b times t. Let's take the ln of both sides. Ln of q of t, I'll just write down ln of q equals ln of the right hand side. But here we have a product on the right hand side. We've log of a product, and that's just can be written as the sum of log a and log e to the b times t. So we've log of product here, so we get the log of each factor in the product and sum the logs. Now the log of e to the power of something is just a power, as we've seen. Now, what are the variables here? Well, we could say that ln of q is the dependent variable. We could call this y. What's the independent variable? Well, it's t. In coordinate geometry, the independent variable is x, so I could write it like that. And the number in front of x is the slope of the line. So the slope of the line is actually b. Now what about this thing here? Well, this is just a constant term. A is a constant. It's the value of q at time 0. It's the initial amount of carbon-14. So the log of A is obviously a constant as well. We can call that c. Y equals c plus mx, but of course that's just y equals mx plus c. This is the general equation of a line. So the slope is the coefficient of the independent variable. Well, it's not x here, it's called t here. This is the independent variable, and the dependent variable is ln of q. That corresponds to y in coordinate geometry of the line in general. Now, m is the slope, and this here is the y-intercept, or it's where the line cuts the vertical axis. Where it cuts this axis ln of q is the value of ln of q when t is 0. Okay, if we put 0 in for t, we get ln of q equals ln of a. So the line through these points will cut this vertical axis at ln of a, and from that we can find out what a is. Now actually it's about here. It's actually 1.38. So this is ln of a. It's the y-intercept. So we can represent an exponential function as a linear function by taking the ln of both sides of it, and the graph of ln of the dependent variable of the exponential function, which is q, against t is always a straight line, where the y-intercept is ln of the initial amount, and the slope is b, the coefficient of t. Of course, it's easier to draw a straight line than it is to draw the graph of q of t, this exponential decay curve. And from the straight line, we can actually get estimates for a and b. So in part E, we're going to find the value of the constant b, so we're going to estimate the slope of the line. We can use 2 points on the line, so I'll use these 2 points, and we have the coordinates of these 2 points from the table. So the coordinates of one of them are 1000, 1.26, and the coordinates of the other point are 2000, 1.14. So getting the slope is straightforward. We just get rise over run for these 2 points. Or if you like, you can call it delta y over delta x. So the change in x here is negative if we go from here to here, but the change in y will be positive. So delta y over delta x will be positive over negative. It'll be negative, of course. The slope of this line is negative. So if we do it this way, anyway, whatever way we do it, it's going to come out to be negative. Okay, so delta x is straightforward. That's just 1000 change in x or the run. Delta y is 1.26 minus 1.14. That's 0.12. So the slope, delta y over delta x, is 0.12 divided by minus 1000. Delta x is actually negative because of the direction I went in. I started here and I ended up here. Anyway, if we work this out, we get minus 0.00012. So this is an estimate for B. And of course, from the previous part, we saw that B, well, from the previous video, B was minus ln2 over 5730. Now to 6 decimal places, this is minus 0.000121. So you can see that we have excellent agreement here. The value that we get from the graph is correct to 5 decimal places. Now in the other part of the question, we want the value of the constant A. So I've explained that already. Turns out to be 1.38 to a very good approximation. Well, ln of A is 1.38. Now if we want to get this more precisely, we could get the equation of this line, of course, and find where the line cuts the vertical axis by letting t equal to 0. T is 0. But anyway, whatever way you do it, 1.38 is pretty good. So to 3 decimal places, A is e to the power 1.38, which is 3.975. So this is the initial amount of carbon 14 in the sample. So at time 0, Q is 3.975, and of course the amount of carbon will decrease. The amount of carbon 14 decreases, so we have carbon decay here. So Q will approach 0 as T increases. If the error in the amount of carbon 14 remaining in a sample of an artifact is plus or minus 5%, what is the difference in maximum age and minimum age of the artifact to the nearest year? Let's suppose that we're dealing with a measurement error here, and that M is the measured amount of carbon 14 in an artifact. So what this means is that the true amount of carbon 14 in the artifact lies between 95% of the measured amount and 105% of the measured amount. Of course, the error that we're dealing with might not be a measurement error. Could be due to something else, but anyway, it doesn't really matter. M is some known value. We get that from the measuring instrument. So that means that we know the bounds for the true amount of carbon 14. So we can calculate 0.95 m and 1.05 m, of course, once we know what m is from the whatever device is used, and we can put bounds on the true amount. So let this quantity be Q1. This is the lower bound for the quantity of carbon 14, calling it Q1, and that corresponds to some time T1. So we know this value, that's the idea, and we can solve then to find out what T1 is, the time that gives us this value of Q. Similarly over here, I'll call this quantity Q2. So Q2 is 1.05 m, and the time corresponding to Q2 is T2. We're interested in the difference of these times, T1 minus T2 or T2 minus T1. So Q1 T1 is 0.95 m, and we use our formula for Q of T, which is A e to the power of B times T. I'll put T1 in here. I'm calling the time that gives this value, a value of Q of 0.95 m, to be T1. Similarly over here, Q2 is 1.05 m, so I put that equal to A e to the B times T2. I can make m the subject of both of these equations. Now, why do I do that? Well, then I have expressions that are both equal to m. They're both equal to the same thing, so they must be equal to each other. So I can put this equal to this and find a relationship between T1 and T2. So I'll write it down here again. Put it equal to a over 1.05 e to the b times t2, and we can divide both sides by a, so it doesn't matter what a is. Next I can do some rearranging. I multiply both sides by 1.05, so you get 1.05 over 0.95 on the left hand side, and then I've divided both sides by e to the power of bt1, so e to the power of bt1 goes in under the right hand side. So dividing the right hand side, we just subtract the powers, and I factorise out the b, and if we get ln of both sides we can get at the times. So ln on the right hand side is just b times t2 minus t1, and at last I can get at the difference in the times. T2 minus t1 is ln of 105 over 95 divided by b, and we know what b is from part A. b is minus ln 2 over 5730. To the nearest integer, this works out to be minus 827. Let's look at a graphical interpretation of the bounds on the measured value. So let's suppose m is somewhere around here. You can put it anywhere, and we have a time corresponding to m, which we can calculate from the graph, or we can read off from the graph. We can either calculate it or read it off, of course. I'll call that value for the time tm. We have times corresponding to the bounds on m. This time here I called t2, and the time corresponding to 0.95 m was called t1. Now we calculated t2 minus t1. We got minus 827. But of course we're interested in the magnitude of the difference in the times. We don't want a negative answer, so we just make this positive. So that means that the length of this red line here is 827. So we can say that the true value for t lies somewhere between the point t2 and the point t1. It lies somewhere on this red line, and we can see that the measured value obviously is less than 827 years from the true value. So the true value might say be here, and the distance between these values is obviously less than 827. It's always less than 827.